Hello and welcome to this webinar. My name is Andreas Blumauer and I'm here together with Ian Piper. Today we talk about taxonomies and ontologies, the yin and yang of knowledge modeling. There's still people coming in, so I just will also briefly talk about the poll. Maybe some of you participated. I will let you know what the results are. We were asking you, would you call yourself rather a taxonomist or an ontologist? And 27% of you said taxonomist, 8% said ontologist, 27% said both of that, and 38% said none of the above. So that's just a brief overview. So it looks like we have kind of a bit a majority with taxonomists here in this attendee list. And yeah, warm welcome from my side. I will start with a short introduction. My name is Andreas, so I'm the CEO and founder of the Semantic Web company. We started back in 2004. We're located here in Vienna, Austria. We serve, roughly spoken, around about 200 customers, and we're the developer and vendors of the PoolParty Semantic Suite. And that's a software which is very much dedicated to the W3C semantic web standards. One part of that is the SKOS standard, the Simple Knowledge Organization System, which is a standard for taxonomies. And together with taxonomies, you can also manage ontologies with PoolParty to make it up towards a full-blown knowledge graph. And that's something we will today, of course, also talk about. And I will hand over now to Ian, who will introduce himself.
Hi everybody, thanks for coming along to the webinar this afternoon. And here's my little section of knowledge graph. I'm Ian Piper. I have an information management company here in the UK, founded in 2004. And I look after a whole range of clients for mainly building the taxonomies and ontologies and other information management systems. I'm UK director for the PoolParty product, which is one product from the Semantic Web company. And as you can see, I know Andreas.
Thanks, Ian, for the introduction. One small thing about the organization of this webinar. You've got the opportunity to ask questions. Please do so. If feel free to put them into this little form, and we will be happy to give answers either during the session or at the very end of the session. Session will take around about an hour. At the end of the session, we will actually close the, let's say, the official part of the session, but feel free to stay in the room. And then we will also open up the microphone, and hopefully we have a bit of a discussion afterwards about the statements we will give to you during the session. So that would be great to have some of you with us in the room also at the end. There was already one question if the webinar is recorded. Yes, it will be, or is currently recorded, and there will be a version of it on YouTube. So that's all settled. Good, let's roll with the agenda. The brief agenda looks as following. I will start with part number one. I will introduce you the concept of the yin and yang of knowledge modeling. We'll talk briefly about the implicitness and explicitness of semantics and why that's so important to pick the right methodology for your own knowledge modeling project. One other central concept in this discussion is about the knowledge acquisition bottleneck, how to overcome with that, which strategies you could choose, how to introduce, for instance, machine learning to help taxonomies develop faster and on a higher level of quality and expressiveness. And then last but not least, we will see how that will be complemented by ontologies, how those two ways to model the world fits together and will result in a knowledge graph altogether. And then Ian Piper will take over.
Yes, and I'll be talking about how you go about modeling taxonomies and ontologies and modeling knowledge with those in combination, getting the benefits from each of these slightly different approaches to modeling knowledge. And then I'll go on to talk about one specific aspect of modeling knowledge, and that is building content knowledge graphs. Okay, back to you, Andreas.
Thanks, Ian. Good. So let's roll. Types of knowledge models, implicit and explicit semantics. The reason we thought, okay, it would be a good time to bring up this idea and this webinar really was we've observed on the market a lot of discussion in recent weeks and months. So what is the right choice for me? Is it a taxonomy? Do I need an ontology? Do I need both? How does that fit together? One really interesting finding for me when I prepared the webinar was I was just looking up on LinkedIn, okay, how many people are there calling themselves taxonomists and how many ontologists are there? And it was interesting to see that 2/3 of the found persons naming themselves taxonomists are female on LinkedIn, and in contrast to that, ontologists are rather male. Well, the whole idea really is, okay, what is usually done with a taxonomy? It's something you would build to classify something else. Maybe documents could be a usual use case. In contrast to that, ontologies are rather used to define more or less the world and reason about it. Of course, the roots are in various communities. Taxonomies come from a different community, from a different mindset. It rather contains implicit semantics, whereas ontologies more or less always were designed to be used by machines, so that they have to provide more explicit semantics. And now on the semantic web, it's interesting to see how those things come together, how they can complement each other. And since the work usually is not done by a single person, but rather in a team of data scientists, of knowledge models, and so on, it's really important to think about how can we help those different, let's say, people with different mindsets to work together, better to let them work together. So that's the idea behind this approach, the yin and yang of semantic knowledge modeling. Sorry. So, okay. So first, I really would like to introduce the concept of implicit semantics. We all know, of course, natural languages are really expressive. They are universally usable, but they are very ambiguous. So you always need to have a lot of context information, background knowledge, if you want to understand something like Susan observes Mike on a tower with a telescope. Okay, could mean several things. Usually we can solve this ambiguity by introducing background knowledge. So we contextualize something like that, and by that we can define, okay, what's really meant by this sentence. So in that case, for instance, you could or you should know that Susan and Mike are persons, that Michael is maybe the same person as Mike, and yesterday he bought a celestron. What is a celestron? It's a telescope, okay. But even you should know, okay, if somebody buys something, you can own it and use it. So you see, you really have a lot of background knowledge and information at hand in order to understand this sentence. And that's something what natural language really makes very powerful in a way, but on the other hand, of course, extremely complicated to transfer that into a language which can be processed by machines. And I think that's actually what we try to solve here all together. And as we will see in a second, there are several approaches to do so. Okay, one other thing we should understand is this semiotic triangle. It's a pretty old concept, but it's still, I would say, very important to keep an eye on it, because as you can see here, so that's the classic version of it. You've got this on the left-hand side, the telescope, the symbol, which denotes an object. And then you've got an interpretant, and this interpretant is trying to make a perfect, let's say, mapping between the symbol and the object. As a human being, as we've just seen, you have a lot of measurements and instruments for that. But how about a machine? And in our world, it's not just the human beings anymore building those semiotic triangles. It's there's many other actors and agents involved in that, and that's the semantic web really, which is now currently built. And we should see at least which options we've got to make those machines better interpretants. And one way to do so is to make use of the semantic web standards. So for instance, here, this URI you can see here refers to a dereferenceable URI, which is DBpedia. DBpedia is available on the web. It's kind of a nucleus of the public semantic web out on the World Wide Web. Lots of other resources point to DBpedia, and it makes it possible for machines to understand in a way what a telescope is really all about. I mean, of course, it's just artificial, but it becomes unique. It becomes disambiguated in a way. And that's one way to make use of the semantic web when it comes to the question, okay, how can we help interpretants to become more precise with the linking of a symbol with an object? And I think the other aspect we should here bring into this discussion is of course, not only ontologists and taxonomists doing this kind of work. There are lots of other experts involved in this joint effort to build out a model of our world, to build together strong artificial intelligence. There's a very interesting, I would say, convergence now I can observe between data science and semantic web people. Also computational linguists and people working in the field of natural language processing, of course, to create work, and all those approaches now flow together, and that's very promising, I guess. And in a way, at least from my perspective, I can see a bit of a cycle here. So from natural languages, you can derive statistical models. From there, you can derive simpler let's say, models with some explicit semantics, and from there you can build yet another layer on top, which is about ontologies, which then bring in more expressive knowledge models with a lot of explicit semantics. But whenever we do that, of course, we have to keep an eye on the costs and on the feasibility. And as we will see, this knowledge acquisition bottleneck which occurs when those people work together, and also our little robot here, that's probably the most important aspect in this discussion. How can we solve this or come over this bottleneck? So let's take a look on that. Actually, that's again a semiotic triangle. It's, let's say, on a meta level, more or less. So you've got here the symbolic level. In that case, a more complex one, maybe a knowledge model. And here you've got the world, or the object, which is the knowledge domain. It's not just a single object, it's more than that. And in order to make this happen, this linking here in between, we have to work together in different settings. So there are all these different knowledge models working together with the domain experts. So again, actually, we have a semiotic triangle here. And the semantic gap here is obvious. So it's really the Tower of Babel we are confronted with constantly. Domain experts talk in a different language than the knowledge modelers, and they have different ideas of how a model should look like. They use different vocabularies, and that's a first sign of introducing vocabularies. First of all, as a good idea to start with. So if you kick off a knowledge modeling project, it might be a good idea to start first with a vocabulary and not with an ontology. And I think that could be one way to start off, but it's of course at that point not really clear how will we end up with. So which kind of knowledge model is sufficient? It depends a lot on the applications later you want to run on top of that infrastructure, of course. But in any case, you always have this problem here, and that's called the knowledge acquisition bottleneck. So computer or networks of computers need to be programmed with sufficient amount of knowledge before it can begin to learn semi-automatically. And this bottleneck is a problem. And in our days, again, there are a couple of companies promising that there's no need to do any knowledge modeling up front. So it's like, okay, give me your data and we will, or our agents, our intelligent agents, our bots, our machines, will create a knowledge model out of that. No need to do any knowledge modeling. So there's no knowledge acquisition bottleneck anymore. Well, I really would like to encourage you, try it out, find out on your own. If that really works, at the end, you will always find out, okay, there is still some work to be done. It's not just the machines which will understand our work, our documents, and all these implicit semantics that easily. So still a lot of things to do for ontologists and taxonomies, and no worries about, let's say, there's not so much artificial intelligence yet developed as some companies promise. Okay. I would like to bring up a little an analogy here. So how does nature go around similar learning bottlenecks? So let's start here. We don't understand anything. So let's say if you have little children at home, you will maybe see that situation currently also back home. You, of course, repeat certain sentences, and then after a while, this small, young, little human being starts to do kind of a concurrency analysis. It does a statistical model, actually, of what you are constantly repeating, and well, certain patterns will occur, like stove and hot somehow belongs together. It's important. So that's the first step, and that's, as I've said before, very similar how you can teach a machine to understand, so to speak, a little bit of the world out there. Next step would be, I could easily say it's a taxonomical model. It's a lot of abstractions which will be derived from the statistical model after a while, and it's really about abstraction at that point already. So it's a simple but very powerful knowledge model which will be developed at that stage. And from there, ontological models come out. Reasoning will happen. So you see lots of rules and maybe constraints will be introduced, and well, maybe too much of thinking also could lead into not being able to listen anymore. That's what I wanted to indicate by this little joke here. Okay, so that's an analogy somehow how you can teach machines, very similar to the way how human beings develop over the years kind of a knowledge base in their brains. How does it work in the semantic web world? So first, you can derive a co-occurrence model from a reference corpus. So put in any document you have. Of course, it should be as much as possible in a way to make that statistically relevant. And what will be the result is a term word or term network, which consists of relevances of terms. So that's indicated by the size here, and co-occurrences between them, indicated by the by these edges here, and that's already a good basis to do some preparation to make out of that more and more explicit semantics, to come up with a formal knowledge model in a way. So in contrast to that, so let's remember the sentence from before, Suzanne observed Mike, and so on. So this is a model which already has some explicit semantics. It's clear what's meant by the sentence or by this model here, much clearer than the natural language sentence we've just seen before, because it introduces several names for the same thing. It classifies in a way already certain nodes in my graph, like those two nodes are persons or belong at least to the concept scheme person. You see I'm using here a standard ontology which is called SKOS, the Simple Knowledge Organization System, one of the W3C semantic web standards. It's concept-based and it's resource-based. It's already a very powerful way to express knowledge, and we will see in a second that you can even use it to make some reasoning about your knowledge model. And you see by that, so here you have a hierarchy, for instance, of things like a telescope is broader of celestrons, or a celestron is a telescope, and so on. So that already makes it absolutely clear what's meant by the sentence we've just seen before. It's, so to speak, not ambiguous anymore. And if we combine that now with this co-occurrency model we've just seen before, it already indicates how a taxonomy can be enriched automatically by machine learning. So it really learns from the corpus, but you need to have some model upfront. Otherwise, you really will always end up with a very flat co-occurrency matrix, or in a word net, a network of phrases, and but not things, not concepts, not resources, and that's the problem. It doesn't have any explicit semantics, but by introducing SKOS, you will start with a very simple knowledge model where the knowledge acquisition bottleneck is not that, let's say, predominant anymore. So you can start from somewhere. There are lots of SKOS vocabularies around for certain industries, and then you can start to do the magic, so to speak, and the result will be quite good. So you see here you've got a network of known concepts, and then they are enriched by this additional network of terms and phrases. And with that, you can do a lot. For instance, extending your knowledge model or extracting concepts which are not even in your document. So that's kind of these learning loops. We can see here taxonomies work with a tool like the PoolParty taxonomy and the Zorro server. It does text mining. It extracts entities from here. It learns from the corpus, and by this ongoing iterations, the knowledge model will getting richer and richer. And the content manager or the end users and their behavior, so to speak, they will also influence, of course, the corpus learning module. So that's this second learning loop you see here. But it's a learning system with a supervised learning approach. And by that, you can even, as I said before here, for example, Machu Picchu, you would not find it in this document, but it's well embedded in this concurrency model. And by that, you can now explicitly make Machu Picchu explicitly available as a meaningful concept for this document, for instance, although it's not even mentioned, but rather, let's say, the context around it. We call that shadow concept. By the way. And then step by step, you see opportunities, and Ian will talk about several use cases why you should extend from a taxonomy towards an ontology step by step also. But there are lots of ways to do so. And for those people here in the webinar who are not that familiar with semantic web technologies, that's the nice part of SKOS, really, because it's based on the very same data model called RDF. So you can extend this SKOS ontology, the simple taxonomy part in your knowledge model, step by step by other ontologies. So for instance, Dublin Core or the friend of a friend ontology. So that's a really simple extension of my SKOS part. And in contrast to that, you could also see here several ontologies linked to each other with some SKOS fragments still in it. So here, again, going back to the sentence we've seen before here, it really becomes totally explicit. You see here Suzanne observes Mike, and Mike visits this geospatial thing, which is the tower, and he owns this telescope. The brand name is Celestron. Here, for instance, I'm using the Schema.org ontology, which is broadly used on the World Wide Web in the meantime, or the friend of a friend vocabulary, which is broadly used for any kind of social network and organizational stuff. And I introduced here my little own ontology, for instance, so I can extend on the existing ontologies easily and make that available by using, for instance, the OWL modeling language. So OWL, that's a good other keyword, I guess. Many of the ontologists working in that field name reasoning as one of the let's say advantages you can make use of when you extend your knowledge model. Okay, so let's take a look on that. If somebody buys a Celestron, he or she can use it as a telescope. That would be one typical, let's say, way of reason about facts. It's somehow like that visualizable. And what you can do with that is, of course, extremely powerful, because let's say you've got a document which is not talking about optical devices at all, just about Celestron and a product, a specific product there, and still you would like to get that document when you're interested in optical devices. What you can do now is you can introduce a hierarchy of concepts in your taxonomy and discuss broader. Property is an OWL transitive broader. You can define that as a transitive broader in your triple store, in your RDF database, and then your OWL reasoner can infer from the fact that that's about Celestron that it's also about optical devices. So that's one way to make use of OWL reasoning. But you shouldn't forget that you can substitute that. You don't necessarily have to use OWL. You can do that also with Sparkle 1.1. And specifically with the property path definition or specification of Sparkle, which is nicely implemented in most RDF triple stores. And you should see also the advantage here. It's even more performant usually than OWL reasoners. And Sparkle is in a way something which substitutes again the complexity on the modeling side. So still here you can keep your model simple. It can remain on the level of SKOS expressivity, and still you can do a lot of interesting stuff with this knowledge model when combining it with the power of Sparkle 1.1. So that's down here. You see, you just have to put there this broader plus operator, and it will recursively traverse your knowledge graph by that. Yeah, and then I also wanted to point to another way how to combine SKOS and taxonomies with ontologies. For instance, you can combine that with SKOS-XL fragments. SKOS-XL as an extension of SKOS. For instance, you can model things like a geospatial thing, which has the preferred label Switzerland. Has maybe also an alternative label called Swiss Confederation, and you can state that that's actually the predecessor of Switzerland, so it's probably not used anymore even as a name, and it has a specific relation. So those kind of things you can introduce if you use an ontology like here my is predecessor ontology statement together with the SKOS taxonomy model. So there's lots of flavors and ways to combine those two worlds, and never forget about the power of Sparkle in combination. So I'm now really finishing, close to finish my part. Let me take a look on the questions. Don is asking if W3C calls this also shadow concept. So if I have to say clearly no, I think that W3C is not really talking on that level. It's really an application of RDF, and you know W3C is not so much in this application layer. So that was really more our own invention. Yeah, and then there is also another question for Ian, but I think that's done by Ian then anyway. Ian, please make sure you take a look on the question of Niels. Okay, so I'm going back to my last couple of slides, which is about the ultimate goal, so to speak. So if this knowledge acquisition bottleneck is somehow tackled in the most efficient way, you found a good combination of ontologies and taxonomies together with data science approaches, machine learning approaches, and some NLP, you will end up in an enterprise knowledge graph, hopefully. And how does that look like? So there is, first of all, the instance data layer. Very simple in a way. It can make use of SKOS a lot. So you see here there is an example around Venice, and it's somehow related maybe to a square and to a certain museum. So, but it's really concrete things you could start with. And then on top of that, you can introduce schema data, maybe something you have already done in your relational database. You can reuse those schemas, you can extend them by other schemas like schema.org and transform that or transfer that really into the RDF graph world step by step. As a next step, you could introduce typically some metadata maybe around your assets, like digital assets and images. You usually have that. Anything in your knowledge graph can have some metadata around it, which, for instance, indicates the usage rights or the provenance or something like that. You might introduce taxonomies more and more. Here, of course, again, this cost standard plays an important role. Typically, you do that because of building synonyms. Later, you used it for text mining facilities and those kind of things. And as a next step, you might link that to other external data sources or internal databases. There's no need to just look around for RDF databases. You can virtually link it to any API, your knowledge graph, or any database. And even text, of course, and any document will become part of your knowledge graph sooner or later. At least the pointers to them, so any data set or Excel data can become part of your knowledge graph. And here you, for instance, see you can use an entity extractor and link your documents with the corresponding entities of your knowledge graph, and so on and so forth. And as a technical precondition to make use or benefit from that, of course, it's good to have a graph database in place, which can execute Spark queries and understand quite a lot of those RDF standards out there. So that's really a very brief introduction to how an enterprise knowledge graph might look like. So that's the anatomy of that. And I will now really hand over to Ian, and Ian will go into more details around the question how taxonomies and ontologies can nicely fit together.
Okay, thank you, Andreas. We'll have a slight hiatus while I take on the presenter role. Let me just okay, and I'm just going to present. Okay, and I hope very much that you can now see slide 32. Andreas, are you okay there? No, I see.
That's fine.
Okay, grand. Okay, thank you, Andreas. In the second part of this webinar, I'm going to present some ideas about where you make choices between taxonomies and ontologies, and how often it's not an either-or decision, but a blend of both worlds, best of both worlds. And I'll go on to talk about how we can practically implement taxonomies as part of a developing enterprise knowledge graph. It's worth saying initially that, to reiterate the point that Andreas has made, that you may already be getting the best of both worlds. If you're building a taxonomy based on the Simple Knowledge Organization System, SKOS, then you're also using an ontology. And if you use a product like PoolParty, then you can elaborate that taxonomy using custom ontologies, and I'll talk a bit more about that shortly. As I explained in a recent LinkedIn article, which you can pick up here if you're interested in seeing that, one of the key differences that I want to bring out between ontologies and taxonomies is ontologies are really designs or templates or models for organizing information and have the appropriate richness of classes and attributes and relationships. Taxonomy is really a concrete collection of concepts that may be arranged in a hierarchy. In fact, strictly speaking, should be arranged in a hierarchy. If you use a semantic product for managing your taxonomies, then you create a collection of concepts in one or more concept schemes. And concepts schemes are classes within the SKOS ontology. So they're specific individuals that are arranged in a hierarchy, and they conform to the SKOS ontology. In other words, you're already using an ontology when you create a PoolParty taxonomy. But a common question that I've encountered in talking with organizations in these sorts of areas is, where do you stop talking about building broader and narrower concepts in a taxonomy, and where do you start talking about designing classes and subclasses in an ontology? And it can give rise to significant tensions amongst information professionals, as I've found. At one end of the spectrum, we have taxonomists. And by the way, I should mention here that I'm a taxonomist first and foremost, though I'd like to think I've got some ontologist credentials too. But a taxonomist will say, the things we're dealing with are the same kind of thing. These are all teaching subjects, they're all geographical areas, they're all types of audience. And the hierarchy is a convenient grouping that allows you to determine levels of specificity and detail. This thing is a more specific example of that thing. That thing is the more general example of this thing. And the example you see on screen here is a taxonomy in PoolParty, and this is a taxonomy I'm going to come back to several times in this talk, of plants. At the other end of the scale, you'd have an ontological view. Now this is a very crude and very simple ontology, and I wanted it to be like that. But you can imagine that a vehicle is a superclass here, and it is very simple. It has a power source, and it can convey things. Anything that is a vehicle will have a power source and can convey things. But you can imagine subclasses of vehicle, such as cars, and they have a power source, and it's an engine, and they can convey things. And in addition, bring in their own feature of having 4 wheels. Similarly, a bicycle is another subclass of a vehicle. It also has a power source, pedal power, pedals and chains. It can convey things, and it has 2 wheels. So an ontologist will say you get much more information from a system by thinking of it as a collection of classes and subclasses, relationships and attributes, with a subclass inheriting all of the features of its parent class, and is differentiated from it by introducing some features of its own. Now, of course, as with most spectra, both extremes are true, and there's a large hinterland between the extremes. So to try and throw a little bit of illumination on this, I'm going to talk about some specific examples. I'm going to start with a grouping of concepts that fit well with the taxonomy structure. Let's think about a collection of geographical entities. We can think about continents, countries, regions, counties, states, and so on. they're all geographical entities rather than classes and subclasses. You can't say that a city is a type of county or that a county is a country with more features. It doesn't work. It doesn't fit into that kind of model. Also, even within a fairly narrow range, such as Europe, you'll see that United Kingdom and Austria have quite different substructures. And it's very difficult in that kind of environment to create a single consistent ontological model that reflects all of this differentiation. By contrast, a taxonomy allows you to group these things together in a sensible, informative fashion. So now let's look at something at the other end of the scale. A collection of plant species, and this is actually the same as the screenshot that I showed you earlier, and we're going to look at that in more detail. Here's part of the family tree, if you like, that leads down to a plant called a saffron crocus. We can build a SKOS taxonomy of plants in this way. All of the things that are in the taxonomy are types of plants. However, there are additional types of data that we don't get from a simple taxonomy structure. And that's because these plant concepts can also be thought of as belonging to an ontological model. And that model defines a kingdom, a phylum, a class, an order, a family, a genus, and a species. And those are not directly catered for in a SKOS taxonomy. So on the one hand, we have a taxonomy that gives us an easy hierarchy and good tool support. And on the other, we have an ontological model that provides richer information, but it may be harder to work with through poor tool support. So where do we draw the line? The good news, I think, is that in many cases, it doesn't have to be either or. If we use a taxonomy management system like PoolParty, we can construct a taxonomy using SKOS and also apply classes out of an ontology to those concepts. So let's suppose we started with a taxonomy structure. We'd build in concepts at different levels, Iridaceae, crocus, saffron crocus, and use SKOS broader and SKOS narrower relationships out of the SKOS ontology to describe them. And naturally, being SKOS, we can also store other properties. And what we get out of that is something like this. This is a hierarchical structure leading down from here, Liliales, down to saffron crocus. Saffron crocus is the currently selected concept. And we can see that there's a lot of other stuff that we know about saffron crocus. This is not just a string of two words. It's a concept that has a range of other properties defined by SKOS, like definitions, matching concepts out to DBpedia, related concepts, broader and narrower concepts, alternative labels, preferred labels in a variety of languages, and so on. Even Latin, by the way, now. So for many purposes and many organizations, this kind of hierarchical arrangement and the additional properties give sufficient information to enable the use of that concept in classification and in simple knowledge graphing. But this hierarchy doesn't spell out to us that a saffron crocus is actually a species and a crocus is a genus and so on. So what if you wanted to convey that information too? Well, we could construct an ontology. And in this case, I've chosen not to do it by classing and subclassing, but creating three different classes and having specific predicates that link those classes together. So we have family, which has genus, and a genus, which has species, and then the inverse relationships that tie those back together. And we could then create individuals out of that ontology. Now, one of the neat things about a product like PoolParty is it allows you to do both by having a custom ontology that you've created by either importing an existing ontology or creating your own. You can then, out of those, create your own custom schemas, which act as a kind of an intermediary, and then apply classes out of those to your taxonomy. And this is what it would look like for this particular case in PoolParty. So we have kingdom, phylum, species, and so on. with the appropriate relationships specified as well. Then we can apply these classes and these relationships and attributes to concepts in the taxonomy. And this is what we would end up with. A taxonomy structure in blue that's defined within PoolParty's SKOS interface, for want of a better description, and underlying ontology classes and relationships that are then tied together to the concepts in PoolParty. So we're specifying that a crocus is of type genus, and therefore it has species associated with it and is within a family. And the result is that we can get both the simple taxonomist view and also ontological classes, as Andreas has described it, Yin and Yang. Here's the PoolParty view of this, if you like. Once again, we've got our hierarchy going down to crocus, and this shows the taxonomy hierarchical relationships. But we also know that a crocus is a genus, and that's an ontological relationship. And we know that because it's a genus, it also has species. It also is genus of Iridaceae, which is a family. So we're managing to store and use both types of relationship. Incidentally, I've also created some attributes here, which is the another facet of creating custom schemes. So in practice, there's value in taking advantage of both the taxonomic and ontological approaches. The pragmatism and simplicity of a SKOS-based taxonomy enriched with additional classes, relationships, and attributes that derive from an ontological analysis. So now I'm going to move on to the last section, and I'm going to set out some ideas about how organizations, and I'm afraid I'm particularly going to be talking about content-driven organizations here, but what I'm going to say applies, I think, generally to any kind of information-centric organization, how they can move away from traditional approaches to the management and classification of information towards a more content knowledge graph driven approach. Now this slide, I apologize for the garish colors, by the way, but I wanted to bring up the contrast between the different types of information. This is a very simple content model from a content management system. A typical content management system will have content organized in blocks like this for a particular content object. The payload for the content is here. This is the actual content that a human being will read. This is a title. And there are various other things that you might describe as metadata. There's an author name, there's a date, and there are these things which are keywords. But it's worth stressing that these are intended to be classification tags, but the context for these is not defined, and there's no obvious keyword variability control. And so what we see, I'm sorry, let me just go back. What we see are strings, we see words, we don't see context, we don't see meaning. It can be useful to try and graph this out as a content model, and indeed to build an ontology. And this shows you the first kind of tentative steps that you might take to move from this kind of view to more of a knowledge graph. And indeed, you can do this with more complex content models. This illustrates a model called Itter, and this is a very, very simplified version of Itter. For those of you who may be on the call who are familiar with Itter, you'll know that this is a radical oversimplification of Itter. But broadly speaking, Itter provides the idea of a map which contains, as it were, a manifest or a description of its contents, each of which is in the form of a topic. And each of those is a model in and of itself containing other metadata or other properties. And you can see that I've sketched out the beginnings of predicates that one might use in this kind of model. These can be of great value in creating an ontological model, and particularly in providing classes and relationships and attributes that might take you far beyond SKOS. But as Andreas has already described, the real benefits come from looking at how an information model can work alongside taxonomies. And so I'm going to talk through a number of incremental steps that one might take in moving along a path from original simple content models through to an enterprise content knowledge graph. Now, this image here illustrates where I believe a lot of organizations may be working in terms of information or content management at the moment. This represents a content management system, and here's our piece of content in place. But we also have a simple internal taxonomy, which is managed within the CMS, and that is providing our keywords. Now, it may be, if you're fortunate, that those keywords have been drawn originally from a taxonomy management system, and there may be some sort of import process that allows you to bring in a concept out of a taxonomy and then apply that to content within your content management system. But it's important to emphasize here that we're still just dealing with strings, because although we may have a sophisticated SKOS-based taxonomy over here that has URIs and alternative labels and many other properties, the only thing we're bringing in is a string. And as a consequence, we're missing out on the opportunity to build out a knowledge graph. We're also missing out on the opportunity to link this content data in the content management system with other information management systems that the organization may be using, even if those other information management systems are also using a taxonomy management system. So where can we go with this? Well, there's a slight modification that one might make that provides some improvement, and that would be, with your internal taxonomy, don't just bring in the preferred label, bring in the URI as well. Because by having a URI, you've got an immutable link back to your taxonomy management system. And because you've got that, you can also, should you wish to, pull in other information that is relevant for that piece of content. But we could go further than that. Why not, if we're bringing in the URI, and we know the URI can be used to retrieve any of these pieces of content, then why not just store the URI? There's a slight change in architecture here. We've still got a content management system here. We've still got a taxonomy management system over here. But you'll see now that what we're storing internally in the content management system is the URIs for the taxonomy concepts to which we're linked. And the actual linking is carried out by some sort of intermediary system. The CMS content object now has a way to link its URI to the URIs of the taxonomy concepts. And so we have the basis of graphable data. We can say this piece of content has a subject classification, not just a tag, to a concept that has a preferred label of graphene. And a consequence of that move, by the way, is that you need another component in your architecture, which in this case is some sort of intermediary that can plug into the CMS and can also talk to the API, also talk to the taxonomy management system. Provided that you've got well-characterized APIs that within both your CMS and your taxonomy management system, and nowadays most do have such APIs or Sparkle interfaces, then you can build intermediaries of this sort in a fairly straightforward fashion. For example, Fonto.xml is a product, an increasingly popular XML editor that integrates with PoolParty and also with a variety of CMSs. And indeed, there are a variety of what are called power tagging plugins available for PoolParty and a variety of content management systems like SharePoint, Umbraco, Drupal, WordPress, and so on. I want to talk about one further step, though. And before I go there, I need to take a short aside to talk about a topic that we've kind of hedged around within this webinar, but we haven't actually articulated. And that's the idea of the semantic triple. This slide shows our content object again, and also a single concept that is being used to classify that content item. They're linked together, but we haven't really discussed how yet. The how is the semantic triple. You can think of a triple as being a bit like a sentence in English. It has a subject, it has an object, and it has a linking verb. And that verb, by the way, in the semantic world is called a predicate. Now, a human sees that relationship in one way. Human will see applications of graphene is classified with graphene. Any machine, any robot, any machine application that's looking at this will see a linked data view, which has the URI of a content object having a relationship that's defined within an ontology, which in this case I'm calling Tellura model. And the particular predicate here is has subject. And the object is the URI for the taxonomy concept. So we have subject, predicate, and object. And that's a simple structure of a semantic triple, and it's the heart of the simplicity of the semantic web. So back to our developing enterprise content knowledge graph. By this stage, we've completely separated concerns. The content management system only needs to contain content. The taxonomy management system contains taxonomy concepts. Maybe other information systems are also in play. What all of them have in common is that they're uniquely identifying their objects using URIs. And those URIs are being used along with some sort of semantic link, some predicate, to create a semantic triple. And those triples are stored within a triple store repository. Now, this may seem like a huge complication of what could be a very simple architecture. But think about the benefits that you get from this. Because we've got now separation of concerns, we can swap this content management system for any other. All it needs to do is to store URIs for its individual content objects. And we can similarly bring in other information systems and links to taxonomy management systems, or to rights management systems, or to a range of other similar kinds of systems. What they all have in common is this thing, the semantic triple. And what we see here is a very small section for this content object of a triple store repository. All of them use the same content object. They have a variety of predicates pointing to the appropriate objects. But of course, many other things could also point to this concept or this concept. And this content object can have a variety of other semantic predicates linking it to a range of other entities in the system. In a real case, there might be billions of triples like this that would then form the basis of an enterprise knowledge network. And this is, again, a very simplified view of a network of that sort. Centered here, we have our content item. It has semantic links to taxonomies here and here. It may be linked to person information over here, such as has author, Ian Piper. It may be linked out to resources elsewhere. And there may be innumerable other connections that this content object may have that enable it to be compared to this content item, and innumerable other such items. Okay, well, that's just about brought me to the end of my section. In summary, taking this kind of content knowledge graph approach has some real benefits in my view. It allows separation of concerns, giving your environment flexibility in terms of plug and play, reduces dependencies between your systems, facilitates the development of an enterprise knowledge graph, provides an incremental route that you can take from current state. A lot of organizations see this, this fearsome thing, the semantic web, and think there's such a gulf between where I am now and where I want to be. How can we possibly bridge that gap? Well, I hope I've illustrated that there are actually some sensible incremental steps that you can take that help you go along that path. And of course, it illustrates the benefits that we've been talking about all the way through of taking a taxonomic approach and an ontological approach to solving your knowledge problems. And at this point, I'm going to pass back to Andreas to wrap up.
Good. Thank you very much, Ian. So, yeah, thanks to the to everybody who attended that webinar. We're coming to an end. I will briefly give some announcement about 5 events coming up in the next couple of weeks. Semantics conference in Amsterdam in September is probably one of the highlights for semantic technologies in industry, and you will meet there same-minded people, around about 400 to 500 people in Amsterdam. Lots of use cases, lots of interesting projects, I guess you will learn about. I also want to point out that there's a good opportunity to continue to gain some knowledge in this field by registering at the PoolParty Academy. For instance, course number 1, the Semantic Technologies training, you can easily register for free and get certified. So here's a short overview over the curriculum, and then there are 2 other learning tracks if that's interesting for you. I also want to briefly tackle or answer a question we had from one of the participants. It was about how to visualize ontologies, make them available somehow as a diagram. So which ways have we got here? We just take a brief look on the ontology module of PoolParty. So here, for instance, we've got a service model ontology with several classes, subclass, and domain range restrictions, relations between those. Some of them are symmetric, inverse, directed, and attributes which belong to a certain domain, and so on and so forth. So that would be worthwhile to visualize that. A nice way to do so is an online service called WebVowl, Visual Owl. And you see here, you just put the URL of your OWL ontology as a parameter. So in that case, it's a PoolParty generated OWL model I've just shown you in the backend. And that would be the visualization of such an ontology. So for instance, here you can see relation types like inverse, domain range restrictions, union of 2 classes, attributes here, data type property, and so on. So that's a nice way to make that visually attractive. In a way, of course, it's always important if you want to discuss about ontologies to make that available to your team. That's a very useful way to do so. So that was one answer to your question. I'd like to encourage you, please stay in the room if you're interested to discuss with us. Ian will also spend some time. Otherwise, I really would like to say thank you very much for your interest, your time, your attention. And we will now finally close this webinar. I say thank you and goodbye, and also wanted to hand over briefly to Ian so he can also say goodbye.
Thanks, Andreas, and thank you all for coming along today. I hope you found it useful. Feel free to get in touch with Andreas or with me with any other questions, or indeed to stay in the room, as Andreas has said, for any follow-up discussion now. Thanks very much.